Greetings, Algebra 2 students. Today's video is going to be about radical functions. A radical function is a function that is basically taking an nth root of an expression involving x. It could be as simple as this one right here or complicated like this one up here. So we're going to work on graphing the more complicated ones today and writing their domains and ranges. So these three steps I have listed here are the three steps that are good to take to make sure you do a good graph of the radical function you're being given. The first step is to graph the parent function, which is y equals the nth root of x. So whatever root is in the function you're trying to graph, you want to graph the very basic version, whether it's a square root or a cube root, which are the main two we'll be working on. After you graph that function, if there's a value in front of the radical sign, this a represents a number, you're going to graph y equals a nth root of x. And after you graph that, then you'll factor in these h and k shift, which are very similar to the hk we use for parabolas. I don't know if you remember it, but hopefully it'll come back as we go through this. So I want to use these examples to show you what to do, and your homework, classwork/homework tonight is going to be do the examples I don't show you, which are at the third and fourth pages of this, the notes that are attached to the email you got. So let's look at this this first one here that I've boxed in red. All it has is the number a in front. There is no hk, or hk you can think of as 0, 0, meaning there is no shift. But this is y equals 2 square root of x. So the first step is graph the parent function, which is y equals the square root of x without the 2. This table of values I have here, I showed you on the notes you had the first day. The reason we're using these is for x, 0, 1, 4, and 9 is because they're really easy to plug in. They're 0, 1, 4, and 9 are all perfect squares, so their square root of them are easy to calculate, and these are easy to graph points. You can put any x into this function, though. I could put in 5 if I wanted, and y equals square root of 5. It would tell you that y is the square root of 5, which is 2 point something. And that's on the graph. It's just a harder point to graph. So these are just easy points to graph, and in general, when you do square roots, you want to think about what's happening to this set of points, and it's going to help you locate your graph well, even though there's lots of xy's that work. These are easy ones to figure out how they're being changed by these other numbers in the function. So the way these are being changed is the y is being multiplied by 2. So when I did this, I'm saying this 2 is the 2 right here. And all you have to do is take this basic function, the simple one, the parent, and multiply its y values by 2. And these are the ordered pairs on this function, y equals 2 square root of x. You can check one and see that I'm right. For example, if I put 9 in for x into this function, I would have 2 times the square root of 9 to calculate y. Square root of 9, we know, is 3. 3 times 2 is 6, and that's right here. But all I really had to do was take what y was when I just have the square root function and double it, and it's going to be the correct y for this function. So over to the right here are the two graphs of these two functions. In pencil is the parent function, the most basic square root function that you're going to get very familiar with graphing. And in red is my final function. That is y equals 2 square root of x, and that is this set of ordered pairs graphed. And you can see what's happening to every y is it's twice as big as the y of the basic square root function. Now the domain and range of this are listed up here. The domain, and these are the domain and ranges of the ones we did on Monday, which if you looked at the notes that I sent you with the filled out notes, you will see that these are the domain and ranges. The domain is all x's greater than or equal to 0, because if you think of domain, the x-axis is this axis. There are no points over here, meaning there are no negative x's represented on this graph, the red graph. The red graph starts at this point, 0, 0, and carries on to the right, which are positive x's. 0 is a point on the graph. It's right here in our table of values, but if you try to put a point in below 0, you cannot take its square root and get a real number, so therefore There are no negative numbers in your domain. And then when you take the square root of numbers greater than or equal to 0 and multiply them by 2, you're going to get positive y's out, as you can see on this graph. The y-axis starts with negatives down low and goes up to higher and higher positive x's, and this red graph starts at the point 0, 0 and goes up. Therefore, its range is all y's such that y is a real with the condition that y is greater than or equal to 0. So let's move on to this next one. Very similar, except instead of multiplying by 2, we are multiplying by -3 after taking the square root of x. So I've graphed the basic parent function in pencil. There it is. But this time I took these y values and multiplied, that's a times sign right there, times, not an x, by -3, and I got 0, -3, -6, -9. That's a -3. I kind of made a mess. So these points, 0, 0, 1, -3, 4, -6, and 9, -9 are graphed. You can see my points, and then I very carefully connected them with a nice smooth curve. Your graph should not look like lines, because these are not lined up in a single line, and you should try hard to make it look like it's curving, coming out of this point, this corner point, and gently curving out like this. The tail doesn't suddenly zig out in a weird direction. It just carries on in this general trend. If you think of what's happening with this one, is you pick bigger and bigger x's, you're getting the square roots of x as you go out. Same thing here, except it's just -3 times those square roots. So make sure your graphs, try to draw them as carefully as possible. They should look like curves. They shouldn't look bumpy. They shouldn't have weird things happening on the tails. Okay, that's those two. The next example is going to involve a shift. So on the next page of the notes I sent you, there is this function circled in orange. Y equals square root of x minus 3, which means you're taking x and subtracting 3 before taking the square root, and then plus 2 is happening after you take the square root. Here are the steps. First, graph the parent function. That's here in pencil, and it's in pencil over here. The a in front of this graph is 1, so there is no change to the, you aren't going to multiply anything by your y values here because there's no a in front. We can go straight to figuring out this is really step 3, because you don't have to, there is no a, which is the step 2 on, when I'm talking about steps here, I'm going to come back here, I'm talking about these 3 steps. If there's no A, you can skip step 2, and you're just going to be shifting your graph from step 1. And the way you do the shift is you think about this HK, and it's 3, positive 3, positive 2. It's a positive 3 because H is always the opposite sign of a number that's attached to X here. So if it's X minus 3, you're going to use a positive 3. If this was X plus 3, the H would be a negative 3. And then the K is always the same sign as this number that's added at the end. So what I did, the effect these are having is taking every X in this table for the basic function and adding 3 to them, and that's these numbers. If you take 0 plus 3, you get 3. If you take 1 plus 3, you get 4, and so on. And then the Y, I added 2 because this is a change on Y, the K. So we take all our Y values and add 2. Now, if you don't believe these are actually ordered pairs that work in this function, you can try one. If I put 7 in for x, I would have square root of 7 minus 3. That's the square root of 4, which is 2. And then I would have to add 2, and that would get me this 4. So these points all work as x, y's in this equation. You can try them and confirm that. Then I plotted these 4 points over here. So 3, 2 is 3, 2. 4, 3 is out 4, up 3, and so on. This grid only goes to 10, but 12, 5 would be this one. All of these points, these four points I plotted here, every single one of them by this HK shift is being shifted horizontally 3 units. That's this plus 3, so 3 units over. So if you take this corner point here, this sort of starting of the square root function, and go over 3 to the right, and up 2, that's where that point is. If I take this 1, 1 point, that's this one, I shifted it plus 3 to the right and then up 2, and that's this point, and so on. So every point on this pencil graph was shifted horizontally 3 and up 2. That's the effect of the HK on any graph, not just radicals. Excuse me. All right, so let's look at these other two quickly. This video is getting a little long and I don't want to lose you. This particular example has everything happening. We have an A in front and we have an H and a K. I'm not going to spend too long on the basic graph. We've talked about it. The first step was graph that. It's in pencil on the right. The second step is take your y values and multiply by 3. We're graphing y equals 3 square root of x before worrying about the 2 and the negative 5. So I times 3 by all these y's and got these values. These all work in this function. And this green graph is this intermediate step of y equals 3 square root of x. Then I took this table of values and said, well, now I'm going to do the shift of minus 2, minus 5, which is the HK, and the HK here would be 2, negative 5. It's 2 because this is a minus 2, and the K is always the same sign as the number sitting there. So what did I do to get these? I should have written this up here. I added 2 to all of these, and those got me here. And what do you think I did to these greens? I minused 5 to all of those, and that got me to these y values. Now, if you don't trust that they work, you can plug one in. If I wanted to see if 11,4 was a solution, I could put it in. Whoops, except that's not going to be it. What we want to do is say, does 4 equal 3 times the square root of 11 minus 2 minus 5? I don't have a lot of room here. So 4 equals 3 times the square root. 11 minus 2 is 9 minus 5. That's 3 times 3 minus 5. That does indeed equal 4 if you do the math. It's 9 minus 5. So it works. But if you do the shift this way by taking these numbers and adding the H and the K to the X and the Y, you will always get points that work in the function you're really trying to graph. Excuse me. So these purpley points are these final points. So 2, negative 5, that's out 2, down negative 5. 3, negative 2 is out 3, down negative 2. 6, 1 is out 6, up 1, and 11,4 is way over here. And then I very carefully connected these with a nice smooth curve. This is the same shape as this green one. They are both 3 times, things are going up 3 times quicker than the basic function because I have 3 in front. The only difference between the green and the purple graph is the purple graph has been shifted 2 units to the right and 5 units down. Now this last one I'm not going to cover too thoroughly because this video is getting long and I want to give you time to do your work. But we have a negative 1/2 in front, so the first step was transforming the basic function by that. You always take care of that, and that makes everything half as big as it was before. Sorry about my scribbles here. And it's a negative 1/2, so all the signs flip to negatives, which, by the way, you might have noticed on Monday when you have the positive square root function, when you have a negative in front of the square root, it makes the function flip to the negative. All the points are now negative y's instead of positive y's. Excuse me. And then to do the shift, this HK is negative 5, 0. Since there's no number added or subtracted on the outside here, there is no vertical shift. There is no K. So I did not have to change these values. They are right here again in pencil, same numbers. But the effect of the H is all of these are, if you minus 5 from all of these, take those, minus 5, you get these values that I wrote here. So these ordered pairs are my orange graph. This is very messy. I apologize for that. I did it pretty late in the evening. And I'm tired. So that's how you do these. Oh, and the domains and ranges of these are listed here. I'll let you look at those and think about them. I've done some in set notation, some in interval notation, depending on, I just went back and forth to practice both. I do want to point out the y. Sometimes people have trouble with them. This one, this is the domain and range of the final graph, which is the purple. This graph starts at, for x at 2, and it's, the way I think of it is, it's all the points starting at 2 and higher, because it starts at 2, and if I take my pencil and drag it to the right, I would be always on top of the purple graph. If I went this way, there's no purple graph to the left of 2. Therefore, the domain does not include anything below 2. And there's a bracket because 2 is a point we can put in and get a real number out. So it is part of your domain. The range starts at this point and goes up. So it's everything starting at -5, which is the y value of that point, including it. This is why we have the bracket, not a parentheses here, up to infinity, because this graph is going up slowly, but it is going up, and it can get infinitely high, and it can get infinitely wide on the x dimension. Actually, I want to go back to the first page real quick, if you're still with me, and talk about how I wrote the range here. This one confuses people sometimes. This is the green graph we're talking about. The x values, it starts at this point here. The x's are from 0 and above. So if you think about the x values of all the points on the green graph, they all have an xy, right? They all have an xy. And the x's are always 0 or positive numbers. That's what that's saying. The y start at the point 0, 0, but they are only negative. So it's all the numbers below less than or equal to 0. The way to write that in interval notation is everything from -infinity up to and including 0. And that's what this interval is saying. So think of this number line. If I turned it sideways for y, we're saying it's -infinity all the way to 0. That's the y-axis. So that's it. Please do the 3rd and 4th pages of the notes that I sent you, and you can screenshot those back to me as your homework. If you can't finish it during class time, please send it to me by Sunday evening. We will see each other again for class on Monday. Well, not see each other, but we will reconvene, and I will be present for your class time that day. So sorry this video is a little long, but this is tying together the domain and range and graphing square root functions.